Tomasz Mis, Польща. Пане Томашу.
So, yes, thank you very much for the invitation for today. My name is Tomasz Aleksander Mis. I'm from Warsaw University of Technology, where I am a research assistant professor. And I'm also the CEO and co-founder of a small startup, Radium Energy, which deals with nuclear energy, nuclear batteries. And the project I have submitted for this year's edition of Atomni Innowatory is named Clear Sky, which is for the electricity production from irradiated graphite stacks radiation. So this time, Clear Sky doesn't aim to save the entire zone. It aims to concentrate itself on the RBMK type reactor, which still in the quantity of 3 houses hundreds of tons of irradiated graphite, which is a highly deadly substance, and there are still no viable decisions on what to do with this type of substance. Research done within Ignalina 1 RBMK 1500 reactor showed that there are many isotopes inside that are highly beta and gamma radioactive, and actually many of these isotopes do resemble isotopes which are used in something which our company is very much interested in which I'm also personally interested in as a scientist, and it is this time indirect energy conversion of nuclear radiation into electricity. We could harvest this type of radiation, not only alpha or beta as we see on this picture, but also gamma into, we could harvest it in a way which transforms it into visible light or ultraviolet light, and this can be harvested by photovoltaic cells. Therefore, our aim, our goal for this project is the electricity production from gamma and beta radiation from these isotopes from the graphite stack, which is still enclosed inside the reactor vessel. What we have proposed is a new type of rod that can be freely inserted inside the RBMK reactor using its existing openings, using its existing fuel channels. It is highly legally convenient as the reactor is still shut down. It doesn't the rod doesn't provoke any kind of fission reaction. It's practically an upscaled detector so that we do not need any additional permissions. It does lower the radiation level around the reactor vessel as it harvests beta and gamma radiation so that the total exposition for this type of radiation outside the reactor vessel would get even lower. Graphite stack management is crucial for this type of reactor as the graphite is a highly dangerous substance and there are still no decisions on what to do with it. Keeping it actually inside the reactor vessel but simultaneously using it for some other purposes like energy production or experiments is one of the options that we would like to promote, that we would like to endorse. Of course, such upscaled detector, such upscaled nuclear half cell aims for an electricity production. And of course, it's very tempting to assume that we would be able to sell this electrical energy outside as we would have something like a primitive power plant, but no. We first must aim to be able to supply at least some of this electrical energy, for example, to the power plant itself to make, for example, the new spent fuel or the waste storage building partially or fully sustainable and independent from our energy sources. Of course, apart from electricity production, we have the irradiation test of photovoltaic cells, which are crucial for the development of new cells, especially for the space industry. And as photovoltaics are getting more and more active within the zone of exclusion, this can also be an interesting way on how to develop this. As I mentioned, it is highly adapted for the existing infrastructure of the RBMK reactor, as practically there are no stack modifications needed as we aim to use the existing fuel channels. Maybe the top of the reactor would require any kind of modification, but if deemed necessary only. We do not plan to interfere with the core. This is very important in the terms of producing any kind of surface contamination of the rod. And well, interference with the core, if it was allowed for us, would mean that we could try to propose a different method of this nuclear energy conversion into electricity. We could propose the direct method of conversion, which is mainly what we do in our company. But as we wanted to separate our device totally from the graphite stack to minimize the risk of contamination, we would like to propose this gamma voltaic cells instead of other types of cells, so that there is no interference with the core, and the possible surface contamination is minimized. The rod can be lowered down using the refueling machine or on the cranes within the reactor hall. This is not a big problem. There is no induced reaction or neutron emission, so we harvest what it is inside the graphite. And any kind of assisting technology, it means power converters, any kind of connectors, and so on. As we use photovoltaics in such a strange or novel adaptation, this technology is the same or similar to the existing photovoltaic technology, so that we are not building something new here. We are using what already is in the market, so we are lowering the costs. We are using commercial off-the-shelf elements, so it is much more robust and reliable. The core of a gamma voltaic or beta voltaic cell is, of course, the thing which transforms the nuclear radiation into visual and ultraviolet radiation. And it is actually the phosphor or the luminophore that has this job. And in the past years, we have developed something that we named the encapsulated halide resin screen.
Tomasz, I'm sorry, I have to interrupt you. We still see the fourth slide.
Geez, that's not good. So maybe continuing, the halide resin screen that we have developed as a core for these type of batteries incorporates halides, which are generally highly dissolving substances. They're very intense solvents, but we managed to cure them with the presence of water in a form that is solid, non-reactive physically and chemically, and practically seals the halide inside, so that there is absolutely no option that it would escape. And if we build it as a separate element from the photovoltaic screen, from the photovoltaic element, then we would be able to replace the photovoltaic element if it is broken. How do we know that it actually works? We have made previous tests a few years ago exactly with the same type of halide resin screen with a comparative cell above a radio source that has high gamma energy, and we did see a very strong effect that was repetitive. It wasn't just a one-time phenomena that we observed. We observed it many times with every exposition. So clearly the halide resin screen worked, and the cell produced electricity. The cell was very tiny. It was more like a detector. It had to be very portable. So there is the basic question: how could we scale up physically these results, this solution, to something much larger, like the full fuel rod? We can do it. We have already made a very simple approach, as we have determined that the total active area of such gamma voltaic and beta voltaic cell inside a single fuel rod would rise to about 120,000 square millimeters, and that is about 3,000 times total augmentation of the initial surface that was subjected to the radiation in our tests. But of course, this would be quite too simple in its approach, as we have a couple of physical phenomena that needs to be taken into account. First, when we connect many photovoltaic cells together, we require so-called ideal diode circuitry, which helps the photovoltaic cells not to charge their neighbors, but to give the produced electrical energy away, not to their neighbors. And of course, the internal resistance of such group is getting bigger and bigger the more photovoltaic cells we add. And of course, if this is one of the most crucial things, if one of the cells breaks down, then the entire rod would be dead. Therefore, currently we aim to incorporate within the single rod 3 serial groups of photovoltaic cells arranged in a parallel configuration, so that we have 3 parts in a single rod, which can be easily swapped if needed. And of course, it increases the electrical current inside. We have estimated already that the total fuel channel reactor area in a single reactor is nearly 190 square meters, and this is about 140 so-called roof photovoltaic panels. So this area is quite high, and well, it can be considered as a small photovoltaic farm. So, summing up, how could we put the graphite stack to work in our idea? Well, first, of course, based on our extrapolated results, we have to design, manufacture, and conduct a test campaign in the graphite stack environment of a single photovoltaic rod. Of course, at the time, we wouldn't have dedicated power converters and so on. So these are mainly the measurements of what such a fuel rod, such a battery rod can do. After that, we need the design ameliorations. We have to determine whether it was convenient to move in, to move out, to operate. We have to also totally upscale the parameters of the entire set of fuel rods. Then, of course, we have to multiply them in number and search for the electrical infrastructure, which is, as I mentioned, generally based on what we see within the photovoltaic market. So this shouldn't be a problem, and this shouldn't be expensive at all. So as this solution is generally tailored for the graphite stack, the graphite stacks of the RBMK reactors that remain fairly intact, and they are not during physical decommission, as it is, for example, in Ignalina 1 and Ignalina 2, we wanted to propose this project in this competition, maybe to gain some interest in it, maybe to gain some support in the development of this project, as we see it as quite interesting, and so are the reviews. So we really hope that we could do something further, something more with this idea. So that was practically all for my presentation. Thank you very much. I hope it was fairly clear despite some technical difficulties, and I'm waiting for your questions. Thank you very much.